Good afternoon, everyone, and welcome to this Nuclear Equipment Qualification Technical Forum. My name is Sonia Legg, and I am your host for the afternoon. I will be guiding you through this event. Now, we have four extremely experienced guests to speak to you today, and they will be talking about the qualification of components. Now, I'm sure most of you appreciate that the nuclear sector is highly regulated, and whether you're already working in the industry or you're thinking of doing so, it's absolutely vital you abide by the rules. But we're hoping to show you today that you do not need to worry about the process. There are plenty of business opportunities in the nuclear sector if you have the right guidance. So the forum today is going to last 2 hours. We will have a 5-minute break after the second guest speaker, and we welcome your questions. We will be putting questions to each guest after they finish a short presentation. I will be putting those questions, but I very much hope they will come from you. So do please use the Q&A box on WebEx, and we will try and get through as many questions as we can. If we can't answer questions in this forum, we will also do our best to get back to you with answers to those questions afterwards. So without further ado, let's move on to our first guest. He is Simon Yates from the Office of Nuclear Regulation. He is a principal inspector at the ONR and is an expert in nuclear safety. In fact, he's been working in nuclear safety for more than 30 years. So Simon, thank you for being here today. I have a question for you. If I was a manufacturer, like many of our guests here today, what do I need to know if I want to supply the nuclear sector?
Yes, the nuclear industry is quite rightly heavily regulated to protect the public in the unlikely event of a nuclear accident. And some of the qualification requirements may seem daunting at first, but when you listen to the presentations this afternoon, remember that you won't be alone, as there's a lot of support and guidance available. I'm going to start off with a brief introduction to ONR for those of you who may not be familiar with the UK nuclear regulator, and then I'll go on to talk about the regulator's perspective on equipment qualification. ONR is an independent statutory body which was established in 2014 on the commencement of the Energy Act. Formerly, we are an agency of the Health and Safety Executive, known as the Nuclear Installations Inspectorate. ONR is as far removed from the government as possible, and the government plays no role in regulatory decision making. There are two parliamentary acts that enable ONR to perform its duties in regulating the nuclear industry. First is the Health and Safety at Work Act 1974, which covers conventional health and safety, nuclear safety, and introduces the important concept of so far as is reasonably practicable when talking about controlling risks. The Energy Act created ONR and defines its purposes in terms of nuclear safety, nuclear security, conventional health and safety on nuclear sites, nuclear safeguards, and the transport of radioactive material. ONR inspectors are warranted under both of these acts, which provide a wide range of enforcement powers. The UK operates a goal-setting regime rather than the more prescriptive standards-based approach which is used in some other countries. ONR sets out the broad regulatory requirements, and then the licensees must determine how best to achieve these requirements. This allows duty holders to achieve the required high levels of nuclear safety by adopting the practices that are most suited to their particular circumstances. This approach also encourages continuous improvement and the adoption of relevant good practices. O&R inspectors generally don't use their regulatory powers in the first instance. Rather, we like to work with the licensees in terms of persuading and influencing and developing open and effective dialogues. And again, just to reinforce that the so far as reasonably practical or LARP approach is central to the UK health and safety law. So what is equipment qualification? The IAEA documentation includes the following requirement, which defines qualification as the verification of items important to safety, that they're capable of performing their intended functions when necessary in the prevailing environmental conditions throughout their design lives. This definition is reflected in O&R's assessment principles. The qualification requirements that the supply chain needs to deliver are derived in the facility safety cases by the licensee or the duty holder. The inputs for equipment qualification are defined in terms of the safety functions for the individual items of equipment, which are generally defined in terms of the required behaviour and the duration or the mission time for that piece of equipment. And then the service conditions under which specific equipment is required to perform the specific safety functions. These are generally established in terms of normal operation and accidents, otherwise referred to as postulated initiating events. Look a bit more closely at safety functions. They can be broken down into three main types: integrity, stability, and operability. Integrity and stability generally demonstrated by complying with the applicable codes and standards when designing, constructing, and inspecting. And this would be the approach adopted for piping, vessels, and other structures. In terms of operability, which is applicable to electrical equipment, I&C, and mechanical equipment, is generally demonstrated by performing qualification testing. In terms of service conditions, we have a range of postulated conditions that are categorised as normal operation, abnormal conditions or mild conditions, accident conditions, otherwise referred to as harsh conditions. The first two are generally considered as part of the normal design assurance process, but special attention needs to be paid to the accident conditions or the harsh conditions, which typically arise during loss of coolant accidents, high energy line breaks. During such events, temperatures, pressures, and irradiation tend to be significantly different from those which occur during normal operation. So for harsh service conditions, little confidence can be derived from normal factory tests, commissioning, normal operation, and in-service testing, hence the need for specific qualification testing during the procurement and manufacturing activities. Harsh conditions tend to focus on those events with the potential to produce multiple simultaneous common cause failures. As I mentioned, this typically includes locos, steam line breaks. Seismic vibration is typically included within equipment qualification programs, as this hazard can also lead to common cause failure across a facility. Other hazards, for example flooding, are generally addressed by physical protection and separation. Qualification for harsh service conditions is also commonly referred to as equipment qualification for accident conditions. This slide is just photos illustrating the damage that can arise to electrical terminal boards during locos. See the before and after the test. An important aspect of equipment qualification is the ageing in order to adequately reflect the degradation that can occur during normal operation prior to accident conditions. So any qualification must address the ageing occurring from elevated temperatures and the radiation levels, and this is of particular relevance to non-metallic components. The ageing evaluation also feeds in to defining the qualified or installed life of particular equipment, after which the equipment may need to be replaced or refurbished if it has not been demonstrated to withstand the ageing for the full operational period of the particular facility. Through life environmental monitoring also allows the opportunity to confirm the bounding nature of the qualification, and also in some circumstances to extend the qualified life of particular equipment. Mechanical equipment is generally less sensitive to aging mechanisms and the harsh environmental service conditions or the ambient service conditions, with the exception of non-metallic components, for example, plastic, rubber components, lubricants, paints and coatings, and also seismic events. For mechanical equipment, it is often the operational service conditions during accidents that can be more challenging. By operational service conditions, I mean the system conditions, for example, valves needing to operate under two-phase flow and pumps needing to handle debris following accidents. This is just a photo of a valve solenoid diaphragm which has been damaged during a local test. The IAEA defined 3 key phases of an equipment qualification programme: the design inputs, establishing EQ, and then preserving EQ. The supply chain has an important part to play in the establishing the qualification phase, as this is when any qualification testing is undertaken and the qualification documentation prepared to support the licensee safety case, and then for the ongoing preservation activities. If you look at the codes and standards relevant to equipment qualification, there are a range of both international and local standards, and some of the examples are shown on this slide. In the UK, we don't have any UK-specific qualification standards, and the ONR doesn't prescribe any particular qualification standards. It is up to the licensee to demonstrate that their approach is adequate and able to satisfy the requirements of their safety case, whilst meeting the so far as reasonably practical principle. In terms of ONR guidance, the ONR safety assessment principles, which are written for ONR inspectors, but are also available to stakeholders, include a principle for equipment qualification, EQ1, which effectively reflects what's in the IEA guidance document, which I presented earlier on. Currently, this guidance is very limited and only covers concepts at a high level and doesn't particularly draw out the significance of qualification for the harsh service conditions. There's no single source of guidance on developing and implementing an equipment qualification programme. So it's been recognised that there is a need for an ONR technical assessment guide on equipment qualification, focusing on the harsh environmental conditions. This is largely driven by the need of the civil new build programme, but will also apply to existing nuclear facilities with a proportionate application. A draft of the technical assessment guide is currently being produced and will be shared with the Nuclear Industry Safety Directors Forum in due course. So to summarise, 3 key things to remember is that the equipment qualification inputs are determined from the facility safety case. Equipment qualification provides confidence that equipment can perform its intended safety function during normal operations and accident conditions. And finally, equipment qualification must be preserved throughout the lifetime of the facility and contributes to reducing risks so far as reasonably practicable. Thank you.
Thank you, Simon, for a very comprehensive overview there. And I think that gives you a real insight into how important EQ is. And in fact, Simon, we've got a couple of questions for you. I know people are just warming up on the questions front, but do get them coming in. We do value them. But I've got a couple here for you, if that's all right, Simon. So just wondering if the UK has tougher regulatory requirements than other countries. Obviously, you represent them, but where do they sit in that?
Okay, as I mentioned in the presentation, the ONR doesn't actually specify a particular approach. And in general, the principles and methodologies adopted in the various standards are very similar. And the UK licensees are likely to adopt the standards from the equipment vendor's country. Where the UK approach to regulation may alter the requirements for equipment qualification in the UK is through the extent of the equipment to be qualified, the detailed safety functions to be qualified, and the service conditions in terms of pressures, temperatures and radiations, which may all be different from other countries due to the requirements that the ONR places on the licensee in terms of their safety case. Okay.
Yeah, no, great. We will be hearing a little bit more later as well, I think, about other countries and how to operate across the world. But actually, we've got the question also here. What's the ONR's position regarding qualification of commercial off-the-shelf items? That's a very good point. Where are you on that one?
Okay, in terms of commercial off-the-shelf items, ONR recognises that there are clear benefits to licensees in terms of potential to reduce costs and design efforts, and also where there's no nuclear-specific devices available, there can clearly be benefits of using well-proven commercial products, and this could be more effective than developing new items. In terms of the challenges, COTS items, commercial off-the-shelf items, tend to be more complex and often include unnecessary or even unintended functionalities, which can be difficult when trying to qualify. Also, these items tend to have a shorter lifetime before they become obsolete, and the commercial development process may be less transparent, which makes qualification difficult. And also, in terms of maintenance and qualification during the plant lifetime, there can be challenges for the licensee.
Okay, thank you for that. I've got another one here too for you, if you can bear with us. So why doesn't the EQ program cover reliability of equipment? Is that something you can answer for us?
Yes, EQ programs are really established in order to provide defence in depth against common cause failures on a facility. So they're really looking at demonstrating the ability of the equipment to perform following accident conditions. Reliability is something that would normally come out of gathering data from industry over the years to support the safety case arguments, which is an important aspect of demonstrating the overall safety of a nuclear facility, particularly in terms of the probabilistic safety assessment side of things. But that tends to be something that's addressed outside of equipment qualification programs.
Okay, great. Well, I hope that answers that question for our guest. Another one here, do qualifications need type testing approval that is verified by an independent agency, or are they verified by the licensee? Can you help us there?
Yes, there's not a requirement per se for type testing certification. The whole purpose and intent of a qualification program is to set out the requirements of qualification for the supply chain to demonstrate through testing or analysis that those requirements are met, and for the adequate documentation to be produced to demonstrate that. The licensee will provide surveillance, use independent third-party bodies where it considers appropriate to gain additional confidence. So I think.
Okay, and then one more here from our list. Can you explain a bit more about the preservation EQ and some of the key areas for consideration? Slightly changing topic there, but can you help us with that one?
Yeah. Okay, so preserving EQ is one of the key phases of an equipment qualification program, as I mentioned earlier. It's important to determine which installation, operation and maintenance activities are important to qualification, and would expect the supplier to produce preservation sheets which outline particular maintenance activities, component or subcomponent replacement intervals if the qualification life is less than the facility's life. Also, there's a requirement to consider modifications and what role equipment qualification plays in those modifications. For example, if a particular piece of equipment is modified, this may invalidate its qualification. Any new equipment introduced by modification may need qualifying, and a modification may alter the service conditions in a given area, which can affect the qualification of other items of equipment. I think the final part I'd mention on preservation of EQ is the monitoring of environmental conditions during normal operations and any in-service testing and maintenance activities. Firstly, to confirm the adequacy of the qualification, to demonstrate that the qualification testing is in fact bounding in terms of aging and degradation. And also it provides licensees with the potential to extend the qualified life of certain pieces of equipment if it can be shown that the service conditions occurring on the plant are less onerous than those assumed in the safety case.
Brilliant. Thank you for that. In fact, moving from preservation to aging, we have a question here about that. You mentioned mechanical. What about electrical components is the question here. Do you have any thoughts on this area of EQ?
Electrical components are generally more susceptible to the types of aging phenomenon that you need to address in a qualification program. Cabling, you've got the cable coatings, a lot of the cabinets are more temperature sensitive, so the aging tends to become more important for electrical and I&C equipment, very much for that reason. And so a lot of focus does need to be put into qualification for such equipment.
Okay, brilliant. I hope that answers that question for you. And we've got another one, and I think this is quite a good one. Can you summarise the broad categories of equipment that need to be qualified for accident conditions? What about that?
Okay. So, yes. So generally, there's 3 categories of equipment that you would want to consider in a qualification program. There's the equipment itself, which is required to perform particular safety function in the safety case, and that should include any services, so electrical supplies, Hvac, which are supporting, for example, a pump to deliver its safety function. Then there's the equipment which may fail under accident conditions, which the equipment itself may not have safety functions, but if its failure was to affect other equipment that does have safety functions, then you would need to consider qualifying the equipment. This is particularly relevant for seismic qualification. For example, if a crane was to collapse onto safety-related electrical cabinets or piping, then that would be a challenge which needs to be addressed, even though the crane collapse itself may not be of concern. And finally, there's the equipment provided for monitoring during severe accidents. This was something that was brought home from the Fukushima accident, where there were times when the information in terms of the condition of the cores at Fukushima weren't readily available. So it's recognised the importance of qualifying, say, the monitoring equipment, which will provide that vital information in the unlikely event of such a severe accident.
Brilliant. Thank you for that. We do have another one as well for you, if you can bear with us for a few more minutes.
Yep.
So does the ONR consider qualification and training of staff who maintain qualified equipment?
Yes, very much so. In terms of equipment qualification programme, it's a key element of certainly the preservation part of the cycle is to ensure that the licensee has got adequately trained, suitably experienced staff running the qualification programme, maintenance aspects, make sure that the maintenance staff are fully aware of the qualification requirements. And that is something that we would look to gain confidence in on a sampling basis during our routine engagements with the licensee during the operation of a facility.
Brilliant. Well, I think that's probably enough questions for you for now, Simon. Thank you so much for that insight. And we will now move on to our second guest. Now, our second guest is Graham Dick. He is a principal consultant at Pwrs, and he also knows all about the regulations that Simon has been outlining for us this afternoon. But he can help suppliers and manufacturers navigate them. So Graham, how difficult is it to make sure safety requirements are fulfilled in the nuclear sector? Can you help us with that, Graham?
And hopefully I can talk you through some examples. Okay. So following on from Simon, how do we do EQ in practice? Following the explanation of the topic from the regulator's perspective, I'd like to give a commercial overview of how we conduct EQ in practice, the approaches that we use, the opportunities that exist, and the lessons that we've learned supporting numerous EQ programs. So I'm aware that some in the audience are not from a nuclear background, so in brief I'll give a quick recap as to key principles. Obviously, EQ is an acronym for Equipment Qualification, which in itself is a shortened version of EQAC, which is Equipment Qualification for Accident Conditions. So essentially, EQ is the business of providing a heightened level of evidence that certain safety classified equipment within the plant will function as needed under accident conditions. There are some examples on the screen. And the need for the nuclear site license holder to qualify the equipment stems from the requirements put in place by the regulator and then ultimately by the IAEA processes. And as Simon's explained, qualification should always be done in line with one of a number of international processes or codes, typically the French, the German, or the American codes, the IEEE, RCC or KTA. And any qualification work that we would do professionally would be conducted in line with one of those key international codes. But of course, the UK is not prescriptive, so I won't dwell on codes in any specific detail from this point on. And crucially, the qualification itself will be set up to address the system's vulnerability to one of a number of accident scenarios which would have to be identified before the start of the qualification programme. And one of those scenarios would have to look at post-Fukushima requirements. And we've got a quick graphic on the screen there that just illustrates how the evidence that's generated by the EQAC activity feeds into the safety case, so it satisfies the claims that are made in the safety case. So I'll briefly speak about the three main philosophies that are used in qualification within EQ. As a supplier who needs to qualify your equipment, what would you need to consider? Which approaches would suit you and which would you choose? So the one that everybody thinks of first is test. We use a test-based approach where you really can't use analysis, either because the environment can't readily be simulated or because the technology is just not readily understood or it's just too hard to model. We often find that suppliers may already have FAT or FAT data, and they often ask specific questions as to whether they need to go ahead with a dedicated EQ test. But as we briefly just mentioned, FAT data doesn't often adequately simulate nuclear accident conditions, so as such it won't satisfy the claims required in the qualification file. So we have a few pictures on the screen, just illustrating what we can do. But in short, TUV are the largest laboratory group in Europe, and we have most of the capability we need under our roof. So I won't go into exact details to what we have, but most qualifications can be completed without specimens leaving our group, and often without them leaving a specific laboratory. So to give an international perspective, our key facilities are in Munich, Fareham, Scotland, and I think there are pictures on the screen of the Fareham facility. And the key point here is that the MEL laboratory in Scotland is the national laboratory for UK flow measurement standards, with, of course, other national standards being held at NPL at Teddington. So we're well placed to qualify against design basis failures. And of course, seismic. So that really brings me on to the second most commonly used approach. So we've talked about test. The second most commonly used approach is often analysis, and analysis is often regarded as the most flexible approach. So we're pretty much at the cutting edge of product analysis and modelling, not only in nuclear but also in other sectors, with an accomplished in-house team of analysts and programmers. So crucially, I think these capabilities can be used across a range of different areas, and we use them within the group for the investigation of aerospace, medical, automotive and energy sector challenges. And I think the interesting thing about this is that it's amazing what can actually be modelled now, what can actually be simulated using a range of software packages. So the fact that once generated, a model can be updated, adjusted, and the boundary conditions moved means that it's a good way to protect your qualification programme and its timescales against potentially fluid customer requirements. So if you have changed your requirements, an analysis is a good way to qualify, because you can adjust your computer model much quicker than you can adjust a physical specimen. So for environments that are readily understood and systems that are readily modelled, analysis is often the preferred approach. Some of the pros and cons are detailed on the slide. As a final point, for any analytical qualification, software quality guidelines must be followed, and the code that's generated, the programming code, must be made available for inspection by regulatory authorities if requested. And this is one of the problems that we know customers have had in the past, where they've developed products using black box analytical techniques. We've suddenly found that we've had to go back to square one because we can't interrogate the original analysis. So, having talked about test, having talked about some analysis, we go on to the third approach, which is most commonly used, which is namely analogy. Now, due to the challenge of finding suitable images of appropriate nuclear equipment, I've illustrated the analogies using illustrations of cars, bicycles, and other consumer products. But the logic is the same. If you have a project, or if you have a product that forms part of a progressive evolutionary design series with small changes between each generation, you may be able to reuse some of your previous work. So with cars, for instance, this particular series started in the 1940s, and with small incremental changes finished production in the 1990s. So it's likely that if we were asked by a customer to qualify, for instance, the 1980s model, we could possibly look at the 1970s model and reuse some of the calculations, some of the technical information. So that gets a tick. That's a potential analogy that could be drawn. With the bicycles, assuming they were even made by the same manufacturer, well, clearly, both of them have sets of wheels, both of them have saddles, and both of them have handlebars, but that's really where the similarities end. So if presented with a situation like this by a customer, we'd have to advise that an analogy just wasn't appropriate, and a new analysis or a new test program would be needed. So if a previous version of your product was qualified, if previously you were in a nuclear sector or products in your range were qualified, you may not have to go back to square one to requalify, and I think that's a key message. And we're very experienced in this aspect of qualification, because obviously in Germany we are a regulatory body, so we regularly construct complex multi-legged arguments to address justifications similar to these. So just a quick slide. Shown above are a number of different design solutions to the same design brief. So of these solutions, I mean, some of them you may recognise, I only recognise the chassis on the end, but the examples are basically products that are produced by different manufacturers using different technology over a long period of time. And they address the same design brief, they essentially do the same thing, but you really can't draw an EQable analysis between them. So if your product range looks like this, if you have a range of component parts that look like that, it's highly unlikely that you could use an analogical approach to qualification. However, some manufacturers do have ranges of products where this can be applied. And the illustration on the screen shows cars, but it could just easily be valves, pumps, motors, or sensors. If you have qualified in the recent past, you may be able to do so again with limited complexity. But of course, you can only draw an analogy of an existing qualification. You can't do an analogy of an existing analogy. So those are basically the three main approaches that we talk about: test, analysis, and analogy. Separate to that, we sometimes bolster these qualifications with in-service experience, or what would possibly be referred to as an ICBM. Separate to that, there are other approaches which can be used for devices, electronic device services, or programming the smart devices. And these tend to be focused more on production excellence and reliability. But I don't have time to talk about those this afternoon. They would constitute a presentation in their own right. So, in general terms, qualification talked about the three main approaches that we follow. Why is it so important, and why is it so important now? So globally it's important, as it's a cornerstone of any nuclear plant safety, but in purely commercial terms it's important for suppliers, it's important for industry, as it opens the door to an expanding market. So with around 443 stations across 30 countries, nuclear generates a lot of power at the moment. And the consensus across major international studies is that low carbon sources like nuclear need to be deployed at a large scale in order to meet net zero carbon. And a median projection is that output by 2050 could possibly need to double in order to limit climate change to 1.5 degrees. So within the UK alone, the sectors start to increase significantly. Currently, there are 3 new major units that are planned, with 1 SMR. And the generation of carbon neutral baseload, of course, is key to the expansion of other green technologies such as electric vehicles and, of course, hydrogen economy. So at present, the estimated market value for the sector is about 75 billion, potentially with overlapping projects. So we know the sector is set to expand, and we know it's set to expand in the UK, and we know that multiple different designs of station may be used. So having identified the sector is expanding, it's interesting to think about how equipment within an average plant is divided and grouped from an EQ perspective. So the graph on the screen presents a sweeping generalization, and it's not focused on a particular plant design, but it's an effective high-level illustration of general safety class distribution aligned with environmental requirements. So in short, an awful lot of the equipment in the plant is non-classified or non-qualified. But of that is, seismic is almost a universal requirement, which straddles most of the different categories. And crucially, we have quite a lot of experience of doing this, having had EQ files certifying seismic performance by analysis accepted on UK new builds within the last 2 years. So seismic requirements are not necessarily that expensive or time consuming to address. Most challenging nuclear accident conditions would really only apply to class 1 to class 2 equipment, and those would primarily be equipment that would be located within containment, which would have very high temperatures, pressures, ionising radiation, heated steam, so on. So it's a relatively small number of component parts. But the key message is that for most of the equipment, qualification is probably less demanding in functional terms than you may think, specifically for some of class 3, or what we possibly refer to as K3AD if we were using the RCCE code. So if your products are produced according to ISO standards of quality and traceability, you would be well on the way to meeting some of the requirements of some of the less challenging classes. However, it's important to stress that the environments, although they may be less aggressive, the reliability of the evidence produced isn't reduced as a result of the class. So we know the spectre is expanding, and we know we need more breadth and more depth of supply chase, and we know that we need new solutions to certain problems. So history tells us solutions to one sector's requirements may already exist in another sector. The example on screen is a technology migrating from a highly regulated aerospace sector to provide state-of-the-art solution to an automotive problem in this instance. A more recent example would be the adoption of multiplexed wiring systems by maritime and offshore operators using networks of CAN bus and Modbus sensors, as per automotive practice. In fact, sometimes coupled to acoustic flow sensors that have their origins in medical application. And history tells us when technology changes sectors, it's often the benefit of both the sectors concerned. With increased commonality comes larger markets to offset development costs. And this is one of the interesting things we see from a TUV perspective, is that we don't just provide laboratory services, but we don't just work in the nuclear sector. So our key observation as a group that's an involvement in all the sectors shown on the slide is that one of the things that seems to stop technology moving sectors is qualification, and it's the perceived complexities of nuclear qualification. So if we can improve this situation, mutually benefit the nuclear sector, who will have a greater choice of suppliers, and the license holders, who will be able to deliver quicker using pre-qualified component parts. So our experience, having helped customers qualify their products, is that qualification helps you understand your product, potentially discovering new capabilities. And again, there are historical precedents to this. Technology can follow an indirect path, and a final application may not be thought of or even initially conceived at the point of development. As shown on the screen, the ultimate application of the new material was not conceived at the point of invention, and an indirect progression was followed. So a step forward in innovation in one field may be required basically from new technology in another field. So I think we need to keep our mind open to that when we're looking at qualification. So in our opinion, considering nuclear qualification from the outset opens numerous avenues. Why not qualify to very challenging nuclear requirements from the beginning, knowing that they bound all other subsequent applications? And as much as anything, this might actually be the most economical approach. So as I draw this to a close, as shown above are some of the sectors we support that, in our opinion, we feel have comparable focus on reliability and integrity, and from the direct experience contain translatory equipment suitable possibly for nuclear applications. The focus on safety and reliability, of course, is not only with the nuclear sector, but with other sectors, and crucially numerous other sectors have similar requirements, such as green energy, offshore energy, aerospace, automotive, oil and gas, and we have involvement in most of those areas. So in recent experience, we believe there's cross-sector applications that may exist for many technology types if people are prepared to qualify. And general examples could include ruggedized cables, which are resistant to very great extremes of temperature and pressure, telecom systems and control room architecture derived from defense or maritime applications, specialized centrifugal and reciprocating pumps, which are used in a lot of stations now, and motorized actuated valves, a lot of which we know have origins in the oil and gas industry. And finally, as we'll hear about shortly, classified HVAC or HVAC systems, with a lot of modern stations involving environmental containment. Classified, ruggedized HVAC system is absolutely crucial. And we think an interesting extension of this may be the use of thermoelectric cooling devices, such as one that's illustrated. So it gives you a feel as to cross-section of technology that we think that's out there, and that if it was qualified, could potentially find uses very quickly. So finally, some final thoughts. So from our unique position with involvement in multiple sectors, we're well placed to guide anybody through nuclear qualification. We really feel the sector needs greater breadth and depth of suppliers. So we'd strongly encourage you to consider qualification of your products for nuclear applications, and certainly investigate ISO 19443, which is the fit for nuclear requirement, which will give you a good grounding in the requirements you need to comply with. So I hope I've dispensed some of the misconceptions surrounding EQ, and I hope I've inspired you to maybe inspect the sector in a bit more detail and possibly enter into a conversation with us about qualifying your products, and we'd be very happy to help you with that. So hopefully, yeah, supplying the nuclear sector, I think, is something that requires closer scrutiny for a lot of people.
Quite a few questions for you. So in fact, the first one I'm going to ask you is we've got one here. Do you need to qualify the system as a whole, or are we just talking components?
The system whole, yeah. I think Simon briefly talked about this during his presentation as well. So what we're talking about here are functional systems that have a role in typically cooling, control or containment, systems that when they're activated actively bring about a safe state. So what we would tend to do is, although we look at the performance of an isolated component part, we really be interested in the functionality of the entire system. And that can be quite challenging when you've got a system that in its entirety needs to be subjected to a seismic shock, for instance, and it could be a very large installed piece of equipment or piece of hardware. And you've got to think about how you can analyze that, how you can model it, or potentially how you produce a very large test specimen, which, for instance, might have to sort of fit onto a very large seismic table, or might have to go into a big climatic chamber. So the answer is yes, you'd have to evidence the performance of the system as a whole, or that you may be able to investigate isolated aspects of that and maybe build a more sort of cohesive model.
Brilliant. Thank you for that. We've got another one that possibly could have gone to Simon as well. Is there any transferability of previous CE qualifications to the new UK CA marking?
Oh, yeah.
Something
I
you
think
can answer?
CE marking tends to be more for consumer products. So probably
Oh,
I'm
okay.
not the best person to answer that one.
Okay, no worries. Let's move on. We've got one here about for analogy method. If I take two analogical materials, say a mechanical pump for which small weights increase during design, updates, accumulates over years, like for cars, can we still say that the dynamic behavior is the same and that the seismic EQ is valid? At which point shall we change the methodology? That makes sense?
You could certainly
Can
investigate
read
it.
it again?
If you had the information to document exactly what had happened over the design process, you could certainly investigate the changes in materials, the increase in mass, changes in flow rates and clearances, and you could then conduct an analysis relative to the original qualified component, and you could take a decision as to whether the performance was still acceptable or not. But in general, there's a limited number of modifications that will be accepted, and most of the formulaic sort of tabulated approaches to this would allow one or two modifications. And if you have a major modification, as identified, for instance, in the RCCE code, you may have to then requalify from scratch.
Okay, brilliant. And another one, does non-classified equipment in terms of safety, but seismically classified, but seismically classified is subjected to qualification? Does non-classified equipment? I'm not sure I'm reading that right.
There's two different sides to the seismic. There's basically integrity, such that it doesn't topple over and damage something else. And then there's functionality, so it functions before, during, and after a seismic event, which I think is something Simon talked about as well. So you could prove that something is safe by design, that it's definitely not going to topple over through some sort of analysis. But proving its function is possibly a little bit harder.
Okay, and then can old EQ files be reused?
Can old EQ files be yes, I mean, it depends how old they are, and it depends on a number of things, such as whether the manufacturer of the component concerned has moved from one company to another but if the same firm is still manufacturing the component part and the file is still representative, then it should be used as a point of reference. And the key question there is quality and consistency of it, and ensuring that what was actually qualified 10, 15 years ago is actually representative of what's still being manufactured now. So there probably have to be a broader sort of audit that would have to be conducted on that. But in principle,
okay. Brilliant. Another one, lots coming in. Could you provide an example for which qualification by analysis could not be done? Good question here. And thus EQ by testing shall be the only option.
Generally, that would be difficult to model, or something that was relatively new, or something that we didn't feel confident in modeling. And there are a number of those, and there's a number of those that we categorized perhaps as hazards rather than as qualification parameters. Fire in particular is something that's very difficult to model. Generally have to go back to first principles. Some very complex systems, when they're subject to, say, seismic excitation, can be very difficult. Notably, component parts that contain fluids or component parts that contain gases, it can be very, very difficult to model that. But certainly for fabricated structures or structures that lead themselves well to computer-aided design techniques, then a lot of them can be modelled. But there are one or two exceptions, and there are things, for instance, the regulator may not feel comfortable with us modelling, and we may actually have a request to go that's the way I want them to do it.
Mm-hmm. Okay, still more. If the system is under safety important class, then all the items like valves and other specialities, are they also under SIG, precisely?
Ooh, I don't quite understand the question there, Sonia. I think that's a little bit tricky. I might have to pass on that one. I can't quite understand what they're asking.
So we'll get them to perhaps reword that one for us, and we'll come back to you on that one. No problems at all. So let's move on to what about can files from other non-nuclear sectors?
They could certainly, EQ. Okay, so if someone's sort of entering the nuclear sector, they have a component part or a product that's made to very fine tolerances that's perhaps used in maybe another safety critical sector. Could you use some of that work? You probably could if it's done to the appropriate standard. But I mean, if they have design files that, for instance, evidence the duration of time that, say, a pump or a motor runs for, and they've got design calculations to that effect, and they can evidence the consistency of the component parts they're using, then I would think we could use that as part of the evidence. It may not simulate the exact accident condition. That then may be subject to something else in the way of a test or an analysis, but it can certainly go some way towards addressing some of the questions that are being asked. So I would think, I would think in some instances, existing design data could be used to evidence. So certainly lifespan. I mean, it may be that the existing design file contains details of the materials that are used and predicted lifespan of those materials in, say, normal ambient industrial environments. And in that case, it may be able to contribute towards assessment of the aging of the material. So without knowing exactly what they've got, it's difficult to answer precisely, but I would feel that it would certainly be of great use.
Okay, brilliant, brilliant. And one here again, I'm not sure. Per analogy, reversed equipment already qualified in the past. Any thoughts on their qualification requirements?
I'm not quite sure about it. Can you repeat that?
Per analogy, reversed equipment already qualified in the past. Any thoughts on their qualification requirements? I've got plenty more, so don't worry if that's not my.
Right. I'm
Rest
not quite
assured,
what
all
you mean by
questions.
reversed equipment.
Yeah, no, don't worry. All questions coming in will be, if we're not answering them in this forum, we will answer them afterwards. Our guests will look at them all. So anyone that's not getting their questions answered directly, please don't worry, we will get back to you on that. But I have got a couple more we can put to Graham now. So EQ a fibre optic cable, what would be the steps involved in qualifying that?
Yeah, so we briefed about cables, didn't we? I mean, fibre optics would really be used for signals, I would think, or sensors. They're not used for conveying power. So it would really be the durability of the fibres, the insulations, and the casing, I would have thought, in terms of their resistance to deterioration in the environment they're in outside of accident conditions, and then subsequently resilience within accident conditions. So that may involve an assessment of local conditions, so very high temperatures, very high pressures, radiological issues in containment, and then may involve an assessment of durability. So it would mainly be a sort of materials type investigation, presumably followed by some sort of assessment as to whether it's still functional in terms of its ability to carry signals before and after accident in a degraded condition that represents the condition at the end of its installed life. So that's certainly an interesting investigation, and maybe something that could be done with a smaller specimen. I'm not sure that would lend itself so well to modelling. But again, it's very difficult to give consultative advice in something like this. We just ask questions of very limited information. So.
Of course, understood. So one here I think you will like. What is the view on 3D printed components? Is it more difficult to qualify such components?
There is work going on looking at that at the moment. So I don't really want to answer that in great detail, but I know that it's a field that's of interest to some people.
Right. Okay, cool. And then let's ask you one more here. What about modification of a qualified component? We're jumping about a bit here, but what about modification of a qualified component post qualification? Would the component reference file have to be updated?
Yeah, okay. So so it's somebody who has a qualified component part, or they have a qualification file for a component part which evidences its performance, and then they change that component part in some way. Yes, I mean, you would have to assess exactly what the modification is and exactly what the effect that has on its performance, whether it's of negligible effect or whether it's significant. And if it changes its behaviour in any way, then you would have to reassess the qualification, subsequently reassess the suitability of that component for the part it was originally designed for. So it could be a simple substitution of an obsolete material with a new material, perhaps, that's of comparable performance, or it could be something more significant. But if something like that were to appear, it would have to be looked at in a great deal of detail. And I think, as Simon talked about his first part, qualification preservation or the decommissioning, removal and replacement of components or subcomponents when they reach the end of their life, it is a significant part of EQ. So that scenario could come about if something is obsolete and has to be replaced by a new material.
Okay, all right, brilliant, thank you. Even more, do non-safety classified systems require seismic qualification?
They could do, certainly for integrity. You certainly wouldn't want them failing in a manner that would endanger a safety classified system. So that would certainly be part of the classification system, that would be a classification activity that would be done at the inception of a qualification program. So yeah, I mean, if it were to fail in a manner that would endanger a safety classified piece of equipment or something that had a role in or safety claim against it, then it would be significant. But I would think it would generally be an integrity related activity. So it'd really be looking at something's ability not to fall over, something not to collapse or fail in a way that would damage something else. But again, it's quite a general sort of answer, Sonia. These things can be quite complex, but at a high level, yeah, that's yes, I think reasons.
We're all right with high level here. That's great. Thank you, Graham. So I think we've got time for another one or two here. But how to ensure continuity of qualification when specific components on the QPS become obsolete? How can we do that?
I mean, that's very similar to the response that we were just talking about in terms of substitution. You really need to ensure consistency of functionality. So if something is obsolete, then it's a question of ensuring that whatever you replace it with is as functional. So you either qualify a new design solution, or you replace the component with something that does exactly the same job as the part that you were using before. That tends to be an issue, I think, more in sort of legacy state fields than sort of new build activities we were involved in.
Okay, we've got a specific one here. What type of qualifications may be required for qualification of mineral insulated heaters to be used in reactor application? Are there any relevant standards?
Are there any relevant standards? That sounds a bit like a very pointed sort of request for some information. I'd be reluctant to answer that without doing some work beforehand. But I would think you would have to look into that in greater detail, look at the materials that are being used there, and look at the exact environment in which that heater is located.
Yeah, of course. We're still going. If you can bear with us for another minute or two, nearly there. How would you seismically qualify a complex system with regards to compound failures?
Again, that's a very, very large question that would take some time to answer. I think we would do it probably using a combination of test and analysis. So I think we would conduct a series of representative tests, and then we would look at the larger sort of systemic modes of failure using some sort of modelling. And then there are pieces of work similar to that that's going on at the moment. So I think at a high level, that's probably what we would do. But you're absolutely right. Within a very large system, if it's subject to an external effect like that, how do the elements within it fail, and then subsequently what subsequent failures do they generate is a big question, certainly with some of the larger systems that you look at.
Brilliant. Well, I think you've asked plenty of questions, so thank you so much, Graham. And just to let everyone know, if you could possibly use the Q&A box rather than the chat box for your questions, that would help us a great deal. But as I said, any questions we haven't dealt with, we will answer after the forum. So please don't feel your question is going to be wasted. We will be there for you. But we will take a short break now. And in the second half, you will be hearing from someone who already operates in the nuclear sector and has been doing so very, very successfully. And if you're also wondering how to operate in lots of different countries, where there are obviously lots of different regulators, then we will find out about that too. So see you again in 5 minutes' time. So welcome back everyone to the second half of our forum. And before we meet our next guest, I'd just like to share with you the results of a poll we carried out prior to this event. We asked you what the most challenging topics are in the field of EQ. That was just one of a couple of questions we asked. And interestingly, 50% of you said setting up an EQ strategy is one of the biggest challenges. Now, I think that's something our next guest will concur with. Cord Lehman, is Head of New Installations at Friotherm. The German firm makes industrial equipment. It also has a contract to supply Dell chiller units to the Hinkley Point C nuclear project in the UK. It's one of only a few companies in the world supplying the units to the nuclear sector. So, Cord, thanks so much for joining us today. Friotherm supplies lots of different sectors. How difficult was it to make those chiller units meet the nuclear safety standards in the UK?
Well, thank you, Sonia. We are working on making them fitting into the UK project, of course, right at this time. And of course, it's difficult and depends on the requirements in general and takes quite a long time. But let me show and explain with my slides that I've prepared here. So it should come up. There we go. So first of all, Friotherm, what are we doing? We are a Swiss-based company. The headquarters is based in Switzerland, and there is an engineering and manufacturing facility in Germany, and there are service offices in Scandinavia and in France and Brazil. And one main branch and one main product are industrial heat pumps with a capacity up to 20 megawatt and up to 100 degrees C heating temperature of the water. And of course, what we're talking here is standard and safety related chillers for various systems in nuclear applications. So when we talk about equipment qualification, what is the main goal of equipment qualification? What are we looking at? What we have to provide is we have to provide evidence that the equipment fulfills the specified requirements under normal and upset conditions at the end of its lifetime. So we have to show structural integrity. We have to show operability during and after an event. What this event can be, I will talk to this in a second. And what Simon already mentioned is we have to do some pre-aging. We have to preload the equipment. We have to stress the equipment with mechanical, thermal, and operational loads already, bring it to the end of its lifetime condition, and then do the testing for equipment qualification. We have to choose the test conditions conservatively so that they are enveloping the event there, and therefore we really have to test at harsh conditions. And those events can be, for example, extreme environmental conditions like high and low temperatures, ambient temperatures, room temperatures, high and low humidity, abnormal electrical conditions like high and low voltages and frequencies. Of course, seismic events. This is the last test you would do normally. Airplane crashes, for example, that can provide or can pose a certain event. And of course, maybe also explosion pressure waves that can happen, and maybe other events that you need to look at during equipment qualification. So, and how we do qualify, basically, you either choose to build a prototype which is a fully identical replica of the production units, the production unit you want to put into a nuclear plant. And therefore you would build a prototype, or if that prototype is getting too big in terms of size and weight, you may want to look into mock-up models, which are simplified installations, just consisting of a few components that you really need to qualify. But in any case, the prototype and the mock-up model, you must make sure that this is fully identical with what you will deliver to the site. And then you go into testing with the prototype or the mock-up. And the equipment qualification also means that that prototype will operate during the testing, or you agree on not operating the equipment. In any case, you have to choose the harshest condition. If non-operation is more harsh than operation, then you would go with non-operation, or you go with operation if it's the harshest condition then. And for passive equipment like vessels and frames, you would go for a finite element analysis, for example, and do a calculation, and you will not build those as prototypes. So you can save money and time there, but I will drop a word on this in a second as well. So when we look into this equipment qualification, we can see that this developed over the past years. We have a pre and the post-Fukushima era, and in the pre-Fukushima era, I would believe that the nuclear operator had to prove that the probability of an event is sufficiently low to happen, and as a consequence, maybe those equipment qualification approaches were not that detailed as they are today. In the post-Fukushima understanding, we really have to look at each event and have to consider this event even if it is very unlikely. And we now have to prove that the event can be handled, even if it's unlikely, within the restrictions and the regulatory restrictions, and have to ensure that the plant is always safe. So we look into each single event and have to make sure that our equipment is safe. As a consequence, you can imagine that we have a conservative approach for the qualification. We have to look into enveloping tests with the harshest conditions, and into comprehensive tests, lots of tests, and of course into documentation. So this has increased, and this from here we get into the challenges that we look at. So as you can see, equipment qualification significantly evolved during the past years. We have numerous specifications in the market, in the world. We have seen the ASME word, we've seen the IEEE word, KTA for Germany, and RCCM and E, all specifications that provide information, provide characteristics for your qualification approach. You have to look into those. There are different approaches for different type of equipment, and you can imagine that when you go to a different country, you do not have unique codes and standards for equipment qualification. It's dependent on the regulatory requirements from the nuclear body in that country, maybe, or from the operator as well, and of course, depending on the local conditions. And you may also face conflicting specifications, conflicting requirements from those specifications. You have to solve those. In the end, you end up with highly customized test regimes per site, per plant, maybe even in one country. Each site can be different. For example, especially for seismic spectra. You have different buildings, you can see different excitation spectra, and this may require a new or partially new qualification. So some more challenges. The surveillance by the nuclear operator and the regulatory authorities has increased due to a demand for more assessments, justifications, and documentation in the pre-qualification phase. So you have to develop your qualification strategy very properly and derive the procedures and the step-by-step agendas. So the nuclear operator and the regulatory authorities are involved in there. We need to have experts that do all this. It's a multidisciplinary approach involving mechanical, electrical, software engineers, and of course you can imagine those are hard to find. And for the passive equipment, even though you are just calculating those passive equipments with finite element method, still you have to prove that your approach is correct and you cover that event, whatever it is, and you have to discuss your results with the authorities, with the operator, and get the approval for your approach. So it's not an easy task, as you can see here. It sounds easy to calculate, but it can be a tricky one as well. So how do we work through this? All I said, these are challenges, and you can work with those challenges. You can overcome the challenges by, for example, establishing a dedicated qualification team. If you think this can be done just as with a few hours per day and you work on this, it will not work. You have to involve your internal specialists and external specialists as well. You have to read the requirements. You have to look at the site conditions, what is requested, what is your safety classification, and so on, and perform the qualification strategy, and discuss this with the customer, with the operator, with the authorities, just to set the basis for your equipment qualification. It's a collaborative approach that you need, and you need to find pragmatic solutions. Simon already said something like ALAP, as low as reasonable, practical. So you have to find solutions and have to set up the basis for your qualification approach. Involve the authorities, this is what I said already, and don't misunderstand the factory acceptance test and mix it up with equipment qualification. Factory acceptance test is something you do at the end of line manufacturing process, and you show that your product is delivering the figures that you are requested to provide. Equipment qualification really shows that the equipment is good for the specified lifetime. So, and you have to find compromises, maybe due to size of equipment, maybe some component on your product is not good for the whole lifetime of the plant. So you have to find some ways to work around this. And sometimes your test laboratories cannot do the testing as you would like to do them. So you have to compromise here, discuss with the customer as well. And those compromises then may go into the maintenance manual, for example, have some more preventative maintenance to do, but you can work through it. It's possible. So it's nothing that cannot be solved. In a summary, we can say that equipment qualification is not a sprint, it's a marathon. It is achievable when all parties are involved in an early stage. If you get experts around the table, and if you don't have the expertise yourself, then involve external partners who can bring the expertise to the table, to your document, and that can solve those challenges. And after you've done all this and survived, and your equipment is good for production and installation in the plant, then you really know your product, you know the weak points of your product, and you know how to improve your product in the end. So that's a brief overview from my end. Thank you, and open to any questions.
Been through the process, I'm sure a lot of people can learn from that. So yeah, we do have some questions for you. So the first one is, how long does EQ typically take?
So equipment qualification, so if we separate this between the preparation phase and the testing phase, say it can take from 6 months to 18 months in the preparation phase, and testing phase then 6 to 12 months. But this depends on the project and of course on the requirements and how many events you have to think about in your qualification process.
Okay, and then what happens in case a component becomes obsolete during the lifetime of the plant?
So when components become obsolete, you have to requalify them. You have to find a substitute for your components. And if you think about electronic components in the control cabinet, you can imagine that those components can be hard to substitute in an easy way. But in any case, we have to find a substitute, go through requalification with that new component, which will involve aging, seismic, EMC testing, all the things that you've done before. And then you will have a new component that can be installed. In any case, this is something as well that you need to discuss with the operator, how they typically, what they expect. So it's, again, something that needs to be discussed in the end.
Okay, now we've got one here. I'm not sure whether you can answer this one or not. I think it's, how are the margins applied to EQ loads, or how are they established? Is that
the margin on the equipment qualification? This comes from the If this question goes into the direction that we want to answer, how many margin do we add to this event, then this can be for seismic event a factor of 1.5 or a factor of 2, depends on what is inside the specifications from your project. So this is sometimes very specific to the plant, to the operator, and can vary from again project to project. But you are adding something like 1.5 or 2 to your factor, and temperatures and pressures, they want to add something depending on the project.
Cool. What can be done in case the specified lifetime of a component can't be met with EQ?
So if we look into this, I understand this question in a way that what happens if the specified lifetime is like 30 or 40 years for the plant, and your component, like a temperature sensor, is only good for 10, 15 years. This normally just would mean that you have to state this in your documentation, in your maintenance manuals, and then you would need to exchange this equipment after that period of time. And if you have to find a new temperature sensor then, because you can't find the old sensor, then you may also need to look into requalification of that new sensor.
Okay, brilliant. How could, another one here, how could a system as large as a modern HVAC best qualified by test? That makes
Depends
sense.
on how large this is. You can go with a full replica of that specific item, like an air handling unit or a chiller or whatever it is, and put this into the laboratories and do your testing. And if your equipment is just then too big, you may want to go with mock-up models and do some carve out specific areas of your components and do testing with that specific component, which then you get several sub-assemblies, several mock-up models with different components that you want to test, and you perform all those testing, which is of course more intense in terms of producing documents than if you would just test one chiller or one HVAC air handling unit or whatever. If you have several mock-up models, it's more easy to find laboratories, but you have to produce more documents.
Okay, and a couple more coming in. They're all flooding in for you now, Cord. What are the test methods when assessing EQ for shock impact induced RRS, and how are they covered with TRS signals?
I don't know if I understand this one correctly. Shock, we do have seismic testing, what we do, and we put the specimen on the shaker table. And in terms of shocks, we haven't done shocks so far, but it would be the same thing to put them on the shaker table. It will be hard to find a shaker table though. To show the operability when the shock happens. And the shock normally you would not find in a machinery room. I think the shock would come to for example, intake silencer, where shock wave comes from outside the building. So, and this passive part can be calculated with FEA analysis or FEA finite element method. So that's how you would do it for.
Okay, excellent. Other equipment qualification, will it be done by the supplier or any third party agencies available for this? Which of course I'm sure they are. So that's the first part of that question.
So equipment qualification, of course, there are agencies for this. We do it for our customers in-house, and of course we involve external partners as well. May not have the resources on a specific topic, so we involve external partners, and of course we have to go to laboratories we do not have here, and we have to rent those, of course. So, and yes, there are external partners who can help you.
Sure. And then based on your chiller unit size, does the qualification plan vary according to the size?
Yes, it does vary. If the chiller is not too big, then you may want to go with the full chiller during qualification. And the limiting thing in the end most likely is the seismic shaker table. If your equipment is getting too heavy, too big in size, then you may not find a proper shaker table. But if it's small enough, you go with the full chiller on the shaker table, and if it's too large, too big, maybe you carve out certain sub-assemblies and go with those.
Okay, great, understood. So I think this relates to the obsolete component question we asked earlier. Surely if a part is no longer available, then maybe the whole sub-assembly might need requalification due to the adaptation to the new part, changes in seismic effects, voltage, frequency spikes, etc.
So if something becomes obsolete, you have to requalify this certain component, of course. If you increase the weight by a certain figure, then you may need to requalify even a larger part, because forces change. You can just calculate this higher loads in terms of weight by using finite element method. It depends on what component and where it is installed and what the requirements are. And maybe it's very easy, or maybe you have to look deeper into it and do some more calculations.
Sure, yeah. And further, same person, just to follow on, is one way around availability to hold large stocks?
Once again, what was this?
Is one way around the unavailability problem to hold large stocks? So I guess, yeah.
Oh, large stocks. Spare parts is an issue, but if you hold large stocks, you may run into storage problems in terms of lifetime, storage lifetime, especially for organic materials. You have maximum storage lifetime, and for example, ceilings and gaskets, you cannot store them for the next 10 decades or 3 decades. So it depends on the product, and I think too large stocks might not be good to look at.
Okay, all right. There's one more here. I think we've got time for a couple more. What do you think the future of HVAC systems in nuclear plants looks like? Anything new on the horizon?
So for HVAC systems, if we go to the chiller side, we have to cope with the regulation on refrigerants, which is posing some difficulties. What will come in the future? We have the global warming impact of refrigerants in the atmosphere, so we have to choose refrigerants quite wisely. Although it's very difficult to find the right one that can survive the next 10, 20, 30 years. We had quite a change in refrigerant. On the safety side, the safety classification, there was a change or an increase to a more harsh criteria for the safety classification. This seems to go back a bit. So there's a bit of movement in terms of classification of that equipment. And I think and in terms of capacity, I can see maybe a slight increase of capacity, of cooling capacity that is required by the nuclear power plant. So basically, I would say not too much movement, but some we can see.
Brilliant. Well, thanks for that. We do have a couple more here, but I think we do need to move on to our last guest. So we will get back to you on those questions we didn't get time to put to you. We will reply to those. So thank you very much, Cord. That's a real insight from someone who is already operating, in the nuclear sector very successfully and across jurisdictions. from Europe in the UK, and we can hear now all about how you can operate in more than one country with more than one regulator. And Dr. Thilo Voss can help us here. He's the business line manager for nuclear power and decommissioning at Pwrs. And he's led many projects related to nuclear safety at home in Germany, where he's based, and abroad. A wealth of experience. And he can share with us some of that now. So Thilo, how difficult is it to supply a number of different countries when they all have different regulators? Thilo, we couldn't hear you for a second there, Thilo, so perhaps you can start again for us.
I'm unmuted now. Oh, sorry. Many thanks. That's the problems in Corona times. No, well, there are really certainly lots of different regulatory systems out there, and you might have experience with them already, or at least you know that. We've heard about that already, that they have different viewpoints on how things are regulated. We had already questions of the involvement of the third party. And for sure, these systems and these things are one reason why equipment qualification looks in the first instance rather confusing at this court. There is unfortunately not a regulation that is accepted by everybody where you can say there's one program that fits all. Nevertheless, having been involved in many of these projects and programs already, I will try now to give you an idea why sometimes the two programs look so difficult and how you can navigate through them without any bigger, let's say, pain or harm. I hope you can see the slides and that worked. I guess for that, you need a little bit of deeper understanding of what are the real challenges currently, moving from one regulatory system or from one oversight system to the other one, and what is behind all that. One reason definitely is nowadays the nuclear project became more and more increasingly really international and complex. I'll have an example for that later on and tell you what that leads to and what is the outcome of that. Designers and manufacturers need to deal with the regulatory systems across the world, more or less. Wait a second. Sorry, can't move my screen. Just fighting with techniques here. Try to solve that, but it don't work. It's funny. I hope you can see me at least. Okay. Yeah, designers and manufacturers need to deal with different regulatory system authorities, design code, and technologies. And that means, especially with the technologies, we have a lot of design philosophies behind that. That is also very important for the EQ topic in the end. The safety concepts are really something that leads to different, let's say, assumptions and to different ways how to qualify these things and what you need to do technically there. Let's turn back the clock, let's say, to the 1980s, an ice age in any way. So at that time, there was a lot of new build activities in Europe. Let's draw as an example, maybe just France, because that's a very nice thing to look at. We had this regulatory pyramid here, and you can clearly see at that time, more or less, all these nuclear new builds were done in a very closed system. We had binding nuclear laws and ordinances and stuff like that coming from the regulatory side and, of course, the law side in France. We had safety requirements that were given by EDF, and the new build was done basically with the supply chain with EDF, so Areva or Framatome or Alstom and the supply chain down there. Nowadays, now, look at the new builds we face in Europe currently. We have one in the UK and one in France, of course, and one in Finland. But in fact, these nuclear new builds have to deal with components coming out of many, many regions in the world. For example, Germany, Japan, if we look at the Horizon projects, or elsewhere. And these manufacturers or these component deliverers are used to work in their regulatory frameworks based on their technical knowledge and their technical standards, basically. Moreover, you have nuclear rules and regulations, codes and standards that are involved. Let's say, for example, RCC, or we have dealt already with topics like ASME and other things. And these makes things extremely complicated to align that already. And last but not least, we have now designers coming from elsewhere in the world. Japanese people doing these things. You have a lot of people from France, from wherever you have the guys designing these nuclear power plants. And that leads to a huge misunderstanding in these topics and a cultural problem. And I'll touch that in a few seconds as well, because if you look into Europe already, we have many variety of regulatory systems already. It was touched already by Simon saying ONR has a goal-setting approach, which I personally like very much. But you have also completely different other oversight systems. If you go to France, for example, you will see that the oversight down there is more procedural oriented. So it's very important to follow the processes. And if you go to other countries like Finland or like Switzerland or even Germany, you will find more prescriptive approaches where we have really a set of rules and regulation that is saying what you need to follow, what you need to do. For example, you take a look at STUC, you even have an inspectorate integrated for class 1 components that needs to be integrated in all their work as well. And then last but not least, and that's an important point, moving from one regulatory system to the other one, you need to deal with a different view on how a third party needs to be involved. I had that question already as well. We have the Ukca system, for example, for Hinkley Point. We have AIA systems in Finland. We have an authorized inspection agency that needs to be appointed by the STUC, for example. Or you have even a system like in Germany, where we as TÜVs, it was said already, are more or less the prolonged workbench of our authorities dealing with all technical topics for nuclear power plants. So these are complete different things of an involvement of a third party that you will definitely need. Furthermore, I already said that, and this is not making here any let's say commercial things for any power plants, but in fact, what I want to show here is simply we have on the left side, let's say passive systems. Passive systems, and this was also a question, how can I completely, for example, qualify a complete system? Need other qualifications, of course, than active system, but we have it, for example, in the EPR side. Then we have completely different, that's what I meant with safety philosophies. If you have, for example, a core capture system versus some in-vessel retainment, of course, you will face other radiation fields that your equipment will be qualified against. Last but not least, we have PWRs, BWRs, or in the new world, even AMRs, SMRs, and other technologies that have definitely different approaches to equipment qualification. And that makes all these things, let's say, look a little bit complicated in the first instance. But is it really that complicated? I would say no. In fact, because you need to come back to what is basically the common goal of equipment qualification and start from that. And if you do that, you'll find a golden line for nearly every common Q process in the world. And to help a little bit to enlighten that and to demystify nuclear equipment qualification, I would like to start again with what Simon said. The basis of all of that is, of course, equipment qualification shall help to demonstrate that a nuclear power plant is safe as it is started and, of course, over the time. So from that safety function, basically, we have systems to fulfill these safety functions. And these systems have system functions. So this is basically the design intent that you need to take into account moving from one system or from one new build project to the other one. Basically, below that, all these systems have subsystems or are built out of components that are classified according to their safety intent. And this is the input that we were talking about before that needs to come from the designer and from the safety case, basically. But below that, you usually have, let's say, rules and regulations in the country that can be applied. If you have a system like the system in UK from ONR, you can say, hey, I can use whatever I like to. I just need to make sure that I can argue in the right way. That's of course a very good thing. On the other hand side, we know that in other cultures, it is easier to say, hey, I have something where I can do work and by the book and just tick boxes. Nevertheless, you need to make sure that you are aware of what is the set of rules and regulations you have to take into account. And from that, and from the input where your equipment shall work under which conditions, in fact, from the safety case, it's up to the licensee and the manufacturer, let's say, more or less as a duo to draw the equipment strategy and to draft that, and then to make sure that the regulator is comfortable with what will come out of that. And we had already questions regarding UKCA marking, for example, so with the conventional side. But I think it's very important to have that in mind right from the beginning, to be honest, because I've seen projects really that missed that, and they were struggling a lot in the end. You need to cover both sides. Luckily, and that is also an experience that I can bring in here, is normally the conventional regulation is covered by the requirements on the nuclear side. So we had that already with safety margins and stuff. Normally, the regulations on the nuclear side shall cover that if you have, let's say, classified equipment, at least. And last but not least, what is necessary, of course, is then the technical verification of the relevant codes and standards and the relevant requirements, and that your equipment fulfills that. That is something that will be done according to what already Graham said, with all these things like testing, like analysis, like taking operational experience into account, not only the transferability of, let's say, development in technology, but also is that an equipment that had been working in a nuclear power plant elsewhere for years? What is the experience there of the aging, for example? These are all things that will help you qualify your nuclear experience, your nuclear equipment in the end. And last but not least, normally you will need a kind of certificate issued by a third party or anybody who's involved in the project independently, like a conformity assessment party or a NOVO, to make sure that really your equipment is fit for purpose in the end. So, and we had that already. Let me come back to just one thing, because this is another thing that was asked and that I would like to touch now. The classification of the systems and how can you save money. And basically, equipment qualification is that costs money in the first instance. But of course, it can also help to save money. And the role equipment qualification can play there, I'd like to show with my next slides. And this is definitely the graded approach to safety that was also addressed meanwhile or from Simon. So the defense in depth is directly related to let's say, the proof of equipment qualification. And we'll come to that later on. Defense in depth is a combination of numerous and independent levels of protection. That's the definition behind it. So the idea, if one level fails, the other one will take over. But it is more, it is implemented by sound design solutions. And that's already where equipment qualification starts in the end. It's not the design only of the nuclear power plant, it's also the design of the components that will be used in nuclear power plants later on, that need to be on a sound way and that need to provide a certain degree of safety margins. So that makes it sometimes difficult to use already, of course, qualified equipment or existing equipment and to use it for a special project. It's always easier if you start to design your nuclear equipment, especially for one project, and then try to transfer it first. Nevertheless, it's more again, because defense depths also mean that you have to implement diversity and redundancy principles. It's not like having a car with one brake system, it's like having a car with 4 independent brake systems that all use different physical, let's say, ways to stop the car in the end. And that means not every equipment needs to be qualified across the highest level, in fact. You have certain things coming from the safety functions and the system functions, taking the defense in-depth approach for safety into account, leads to a qualification and classification system of quality grades of your nuclear equipment that allows you in the end to produce and to manufacture equipment that is not of the highest quality, but it is fit for the purpose that it is foreseen for. It needs to play the role in the nuclear game in the end. And I guess that's perfectly really here as well, let's say, reflected in the ALAP principles in UK. Last but not least, that shall demonstrate how important it is to have the right equipment qualification process and strategy in place, because that shall help you to demonstrate that your equipment is fit for the purposes you foresee. So you will not all produce components for a safety class 1, basically, that is of the highest level and has to fulfill the highest safety functions. You need to qualify your equipment in a way, and we had that already. Do we have equipment that needs to be qualified for seismic if it's not classified? And Graham's answer was perfect. The answer is yes. If it can hurt or if it can damage anything that is classified, it needs to be, of course, resistant to seismic. But in fact, the component itself may fail. It just doesn't need to harm anything else. And that's the important answer. You need always to make sure, what is your equipment foreseen for? What shall it do? What is the safety function it has to fulfill? And from that, you need to draw the right principle or the right, let's say, specification and the right setup for your equipment qualification. And that will help you in the end really to balance the cost versus quality. And I'd like to say one more thing, and that was touched already as well by Cord, and is here again in my summary as well. It's very important to get all stakeholders on a round table very early in the race. Why is that so? Let's take the cost example, for example. One thing that nuclear new builds nowadays really suffer from is that you have to do a lot of rework. If you start that and you have to do things 3 times, 4 times, 5 times, and believe me, I've seen revisions of P for the specification of nuclear qualification. That is definitely something that is not planned in the beginning and is a cost and time overrun that will cause that. If you have the stakeholders on board right from the beginning, that shall help you to avoid costs in the end. And it's really, there's many things that you can easily see. If you find errors late in the race, you will see that they cause normally more problems and more costs. If you find the errors early in the race and can do countermeasures, implement countermeasures there. The other one is, there is really not one EQ strategy that fits all nuclear power plants. That's true. So you need to transfer the knowledge, and this is also very important, Corte. If you have done that once, you're very familiar with your equipment, and you know how the processes run and can be transferred. So I would like to see EQ as a kind of excellence model. You can really gain excellence, and with that excellence, you should be able in the end to transfer your equipment from one nuclear power plant project to the other one. That's the important thing in the end. The underlying EQ process is basically the same. It's always the same. You have temperature, you have humidity, you have earthquakes, you have all these things, and you need to qualify your equipment against that. You just need to find the right setup and the right conditions, and that makes it so complicated in that especially regulatory system. But in fact, my advice would be, try a competent partner, experienced in that field, especially in that area where you intend to deliver your nuclear components to. Involve the stakeholder early. Don't forget the third parties, please. I'm from a third party, so I can tell you that this can really cause headache late in the race if you haven't involved these guys early. And there's help out there. It's a marathon, it was already said, but I guess there are people that can help you to win that marathon. Many thanks.
Brilliant. Thanks, Thilo. That was excellent and really good advice there. And it looks, you know, you don't have to worry too much about that process if you get a little bit of help. So thanks for that. And we have some questions, of course we do, for you too. And the first one, so if a component is already qualified for a specific project, is this qualification transferable to other projects with lower requirements, perhaps regarding seismic requirements?
Yeah, that's perfect. Yeah, indeed. And I guess the important point here is the lower one. It's already like Graham said, that these questions are complicated. In general, yes, but you see, if you look, for example, at seismic requirements, seismic is something where you have loads over a frequency band, basically. And if all loads are covered and over this frequency band, normally it's, let's say, a conservative way to really qualify your equipment. And of course, if that is done correctly, you can transfer that. If you have the situation that was also addressed already, that, for example, you change parts, and of course, then the mass of your component will change, or with that, the eigenfrequencies, for example, that will be difficult then to make it transferable and maybe need a new qualification. Or if on the frequency band, some frequency are higher, or some, let's say, or some loads at special frequencies are higher, then of course you might run into trouble and need requalifications.
Brilliant. I've got a couple of questions. Well, I think 2 people talking about the laboratories. So what about the labs where the components are qualified? What can you tell us about these? How many labs are involved in EQ? Are they all in the UK?
I guess there are. Graham said that already, so I can just answer from TÜV Südside. We are running several labs from TÜV Südside in UK. It's Farm, it's the NEL, basically. We have partnership networks there to do that equipment qualification. We've done that already in many other sectors, basically like aerospace and like oil and gas and stuff like that. We have a network of labs already around the globe as to Süd. We have very experienced labs as well in Germany. We can't cover everything, for example, that needs to be clear as well. There are certain labs that need to fulfill certain conditions, for example, regarding irradiation. That is not, unfortunately, not in the family of Süd. But basically, with our partnership network, we can have to find a solution for that. It's up to you. Sometimes it's easier to use a lab in UK. Sometimes it will be easier to use labs outside the UK. That's what I said. What you need, in fact, in the end, is then, let's say, a piece of paper saying, yeah, it's done after the right, let's say, in the right way. And you need to have a good equipment qualification specification or plan or whatever strategy that needs to be agreed with the regulator and the licensee in that way that it is accepted and that you fulfill all what you need, and then the rest is finding the right lab to help you. But this should be doable.
Okay, and you can help find a lab for someone as well. It's not that, you know, manufacturer doesn't have to find it themselves. You can help with that.
We don't have it in-house, basically, so we have some in-house solutions and possibilities as well. If we don't have it in-house, usually we work with partnership labs and things so that we can, yeah,
okay.
help.
Okay, one's just dropped here, haven't quite read it through. For qualification of a sensor consisting of many individual components, is it okay to qualify the whole sensor, or do you have to qualify the individual components?
That depends on how you, let's say, use that in the end. It's again the same question we had already. It's a difficult question. Basically, you can do both. You can either, it depends, let's say sensor yield normally is not that big. So my idea would really say the sensor itself fulfills, let's say, a safety function or has something to do, fulfills a safety related function within the system. So I would qualify the sensor as a whole. But if you want to sell, for example, parts to another project, it might also make sense to qualify parts of the sensor first. So it's a little bit difficult to answer that question. But in general, if one sensor is foreseen for one nuclear project, I would qualify the sensor as a whole.
Okay, brilliant. And then can you speak about accelerated aging, particularly with acceptable methodologies?
Yeah, that's a good point. Actually, it's a difficult one. That is preserving EQ a little bit. In fact, of course, it is. As I said, EQ is important in the complete safety concept of a nuclear power plant. It is important to make sure that the equipment does not only work in the first 5 minutes and then afterwards it will not work anymore. So you need to make sure that you have a certain, and this was also already asked well, reliability of your nuclear components in the end, so that it will work after, let's say, 40 years in the same way it is foreseen than it is at the beginning of the lifetime of a nuclear power plant. And you usually do that with an accelerated aging, for example. Yeah? That means, for example, if you have a certain amount of radiation, yeah, you put that into a radiation field that is higher than where it is foreseen later on, so that it collects the dose in a very short time. And then you can see what is the embrittlement, how does that work? Or take aging, if you have, let's say, take corrosion. If you have corrosion over a long period of time, you can use, of course, harsh environmental conditions with salty mist, whatever, yeah, to accelerate the aging, and then see how does the nuclear equipment work after a while under these harsh conditions, to get a feeling how it will work after, let's say, 40 years operation in a nuclear power plant close to the ghost line. This is the idea of accelerated aging, and yeah, it's a good concept. We use that. I would combine that always a little bit with operational experience of similar components somewhere else in the world, if you have it. If it's possible, that's always a good thing to do. Say, hey, I have a similar component. We've seen that the accelerated aging really reflects the situation the component will be in after a while. And this is a perfect combination, I'd say, to use that concept for accelerated aging. I hope that answers the questions. If not, please feel free to send in another question.
Okay, we haven't got a follow-up to that yet, but let's go to another. I think this is a really good broad question. What are your major recommendations for a new operator as a beginner?
Oh, good. Really good question. Same then for the manufacturer and for the designer. Basically, get in touch with somebody who helps you to sort all these things. I guess it's always just confusing. An operator has maybe one big, one thing that eases his life, let's say it like that. He's just operating his nuclear power plants usually in one country. So he needs to be aware of the regulatory system there. He needs to be well aligned with the, for example, in UK, the owner with Simon, he needs to have his connections there, and he can build up his network. And that's what I would definitely recommend, to focus then on that, on your country first, because operators normally don't operate nuclear power plants in several countries, besides some, but usually that's a local thing. So concentrate on the local situation, get the right partners on board, and see how that all shall interact. And I guess that's the good starting point.
Brilliant, good advice. I think maybe that's sort of slightly linked. What are the different roles of the designer, the operator, and the equipment manufacturer?
I tried to illuminate that a little bit with that slide here, because here you can see what I would say is the role of each. So the licensee and the designer need to bring in the intent. What is the equipment for? They have to deal with the safety functions and the system functions, actually the related ones. They have to bring in the input from the safety case side. This is basically the role of the designer and at least the licensee in the end. Then I would definitely always see a strong link for the equipment qualification strategy between the licensee and the manufacturer, because they need to set up something they are both confident with and that works in the end. And again, I would strongly recommend already at that stage to get in touch with ONR. Simon said that they are open to have that discussions, because if the strategy will fit, then it's far more easy in the end to really draft or write the equipment qualification specifications, and to make sure that you don't run into costly rework afterwards. And last but not least, of course, it's the manufacturer need to qualify its equipment, but he can do that with partners, so he can involve third parties, test houses, stuff like that, buy in some help from that side. So this is then something that needs to be done from the manufacturer side. I hope that answered that question.
Brilliant. I've got one more I think we can probably finish with. So bear with me on this one. EQ programs are against a design life. Presumably life extension will be considered in the future. How can we future-proof the EQ file?
Very, very good question. Basically, we have that situation, some experience with that, or in many countries around the world. We've seen many, let's say, lifetime extensions now from 40 to 60, from 60 to 80 years, or now in France with some maybe lifetime extensions for the next 10 years. The good thing is that equipment qualification is foreseen, for example, for 40 years. Easiest thing in Germany. If you would have said now we run into a lifetime extension, you have aging programs in place, and the aging programs will see how much of your intended lifetime is used already, let's say like that. So you have I'll give you an example. For example, the usage rate of the reactor pressure vessels in Germany was about below 10% of its original intent, design intent. So you have 90%, you would have had 90% margin if you wouldn't have closed the reactors down. But in fact, you can definitely say there is a certain set of load cases, which is the design intent. And if you have a good aging management in place, you can just count the load cases, for example. That's the easiest way to do that. There are many different ways, but just to give you a feeling and say, hey, my component has seen over its lifetime up to now 5 of the 15 intended load cases. So I have 10 more left, basically, and I have a certain kind of margin in them. And that can also help you then to be used and say, yeah, the equipment is fit for another 10 to 15 years. You have maintenance programs, of course, like Cord said. So it's not like you implement your equipment to the nuclear power plant and will not see it for the next 40 years. Usually you have your outages where all the really essential components are in maintenance programs, and you can definitely see what are the parts that have a high usage factor that needs to be replaced, for example. What are parts that are of a low usage factor that you can definitely use. You have, for example, non-destructive testing methods where you can see is the component still in a good shape or not, and stuff like that. And these all together will definitely then give you a good basis to decide, yes, I can use that component for the next 10 years, or no, I need to replace it in the end. And I had a question that I'd like to answer, maybe aside that, where the differences between electrical components and mechanical components. Normally, there's one interesting thing that I've experienced from my operational experience, more or less. It's easier, of course, to change an electrical equipment if it's not the cabling itself, than to exchange big pumps or pipings. You can do that as well, but normally, for example, if you have a seismic qualification for a complete piping system, it's hard to say, I just cut the part and then put a new one in, because the requalification of the complete system needs to be done again. But it's sometimes easier if you just, let's say, exchange a blade or something like that for an electrical equipment. So normally electrical equipment is easier to change over the lifetime, but nevertheless, the new one needs to be qualified as well.
Brilliant, thank you. That's a really, really good place to end, I think. Thank you, Thilo. That was some excellent information there and some great questions from our audience as well. We will have to leave it there today, and thanks again for contributing to this forum. Excellent contributions, and as I said, we will be getting back to anyone whose question hasn't been answered. But I really hope that we have demystified the equipment qualification process for you a little bit today. And I hope we've also encouraged you to consider offering your expertise to the nuclear sector. Just before we leave you, I would also like to encourage you to join the Nuclear Industry Association. It's the trade association for the civil nuclear industry in the UK. A membership gives you access to a range of useful business groups, webinars, and industry news. And finally, I will leave you with the contact details for all of our guest speakers today, should you wish to get in touch with them or their organisations. It's been a pleasure hosting this event today. Do enjoy the rest of your evening.